For this last new section of notes in this unit, we're going to talk about two sample t-tests. Just like before, that we're going to mainly focus on the t-test aspect, the steps, the conditions, and calculations that would be the same if you had the z-test option. And once again, that would only be true if you had the population deviation instead of the sample, but that's fairly unrealistic, so we won't go too much into that. Just know that if something should come up where the population deviation is known, everything else would follow, other than using population deviation instead of sample, instead of using the z-chart instead of the t-chart, everything else would be the same. So our conditions for the two-sample t-test, we need both samples either need to be random or both treatment groups need to be randomly assigned in the case of the experiment. And note that all these conditions need to be checked for each one separately. So for the normal condition, you need both populations need to be stated to be normal, or both samples need to be at least 30, or both of the graphs show either linearity in a normal probability plot or an approximately normal shape on a histogram. For independence, once again, each of the samples is less than 10% of their respective populations would be fine, or each of the treatment, within the treatment groups, the individuals' results should not affect or influence one another. Right? Our test statistic is going to be a t, once again, because we're dealing with sample deviations. So it's going to be the difference of the sample means, okay, so this will be given to you, minus the difference of the population means. Keep in mind, our null is going to be something along the lines of mu1 equals mu2, very similar to the proportions last section. So really, if our null is that there is no difference, and mu1 minus mu2 is 0. So you'll see this in the textbook, the difference between the sample means then minus 0 typically at the end. If that bothers you, you don't have to write it, but that is just to follow the pattern of the rest of the t and z test statistics that we've calculated so far. Then we have the combination, the standard error of the combination of the distributions, so standard deviation, or the variance squared, the variance of the first one over the sample size of the first one plus the variance of the second one over the sample size of the second one, all under the root. And then you would go to the t-table with the degrees of freedom. Now with two samples, you have a couple of options. If you are using the formula and chart method, that's the way you like to do best, your degree of freedom will be one less than the smaller sample size. So if they're the same, it doesn't matter. If they're two different sample sizes, you just take one less than the smaller sample size. That's the conservative estimate for the degree of freedom. That'll give you a larger value on the chart. So it's considered the conservative estimate. If you use the calculator method, the calculator uses a big ugly formula involving both the sample sizes and both the deviations in terms of the size and the spread of the samples to calculate a combined degree of freedom, which is usually just a little below the sum of the samples. So if you're going to use the calculator method, make sure to state its degree of freedom and t-value and p-value. If you use the chart method, use the conservative estimate for the degree of freedom and then t-value and p-value. So just stay consistent, basically. Okay, before we get into any examples, just real quick review, matched pairs versus two samples. Matched pair is when I have comparing different results within one population. So I'm looking for the average difference. So I have the reflex rate for both the left and the right hand or of individuals, or the pre-test and post-test of the language teachers put into an immersion program. Two samples when I have two different populations, so men versus women, Democrats versus Republicans, older people versus younger people, and I'm trying to calculate the difference in averages, so subtle difference in the wording, but it is there. So for instance, Democrats versus Republicans over anything that's two different populations, that'd be a two-sample test. Testing two different variety of corns, where I have 10 plots. The plot is split in half, and then planting one of each variety on all of the plots would be matched pairs. Men versus women on migraine medication or anything would be two sample. Reaction time between caffeinated and non-caffeinated students would be matched pairs if each student does both. However, if I had a large group of students and I just assigned each student to one treatment group, then you consider two treatment groups, it would be two samples. If there's some, the difference in the populations would really just be that they had been allocated to two different treatment groups. That is considered two different populations. IQ scores of low versus high income kindergartners would be two sample, and then pre-test and post-test scores of a language immersion program would be matched pairs. Okay, so first example all the way through. We have information about some heights of 10-year-old girls and boys, the mean and standard deviation from the sample given. And we want to know if that gives us evidence that there is a significant difference in the height of boys versus girls at this age. So I wish to test at 5% significance the hypotheses that the null where mu1 is equal to mu2 versus the alternative that mu1 is not equal to mu2 because it just says is different. Okay, and then define mu1 and mu2, where mu1 is the height of 10-year-old females and mu2 is the height of 10-year-old males. You could use different subscripts that would be self-explanatory here. So F for females and M for males, or G for girls and B for boys, and not have to do as much explanation here. Okay, our type of test is a two-sample t-test because I'm talking about two different populations here. Both of the samples were randomly selected and can be considered independent because the samples are very reasonably less than 10% of their respective populations. And then the heights in this case for boys and girls, heights in general, are generally expected to be following a normal distribution. So it was stated in the problem, they follow a normal distribution, so no further work needs to be done, which is good because too small of a sample to use a central limit theorem and no original data to do a graph. Okay, so I have my do step. You could go ahead and write the degree of freedom if you'd like to get that out of the way so you don't forget. Smaller sample was 8, so we'd have 7 degrees of freedom if I'm using the formula method. For a t-test statistic, I'm going to make sure I subtract in the same order, so whichever one I have defined as mu1 needs to come first. So this is the average for the 10-year-old girls minus the average for the 10-year-old boys. This is from the sample, minus 0, which is what we expect our difference in the population to be based on our null, over the standard error for the combined distribution. We get a t-value of positive 0.45. Just like last time, if we had gotten a negative, we would use the positive version. We would have used the absolute value of it. So we need to find where on our AP formula sheet 0.45 would fall under 7 degrees of freedom. Okay, so 7 degrees of freedom, 0.45 is actually below to the left of any value that we have on the chart. We'll take a look at what that means for the p-value. The lowest p-value we have is 0.25, and as you can see, going to the left, it's getting larger and larger. So that means that our p-value must be larger than 0.25. In addition, this is a two-tailed test. It's a not equal to. Remember, not equal to, you always need to multiply by your p-value by 2. So it's actually, we know that the p-value is not only bigger than 0.25, it's actually bigger than 0.5, and that is important. And once again, that's because of the not equal to, we need to double it. Okay, I'm going to pause here and just look at what this would be for if we was using the calculator version. I would go into the two-sample t-test in my calculator, plug in the mean, deviation, and sample size for each, choose the not equal to version for the alternative, and then of course always say no for pooling. And here's the printout of what I would get. So there's my t-value, which is the same as what I got from my formula, my p-value, which is a little bit more specific than what the chart gave me, and then my degree of freedom based on the big ugly formula that you don't need to know how to work with. So notice, like I said, it's a little bit less than the sum of the sample sizes. Okay, so either way, whether you use the calculator or the formula method, we can make the same conclusion. At 5% significance, we fail to reject the null. Therefore, we cannot conclude that there is a significant difference in the heights of 10-year-old boys and girls based on this data. Okay, another example, looking at whether calcium would reduce blood pressure. Okay, so the previous studies had shown that this relationship was strongest for Black men, so we're going to recruit subjects of that gender and ethnicity to take part in our experiment to make our standard deviation as small as possible. We want to get a very specific group. Okay, so we have 21 people that were recruited, so they were randomly assigned to either calcium or placebo. Notice that I have a slightly different sample size, and that's okay. Be careful here, just looking at the chart, it almost looks like matched pairs. But when I read it, it's just being randomly assigned into two groups. They were not paired in any way. And in addition to that, since I have an uneven group, I can't have matched pairs because there's no data for this last number to pair with. Okay, so I'm going to have my null is that there is no difference in the blood pressure between the two groups, and my alternative would suggest that the calcium group would have a bigger negative response than the placebo group, meaning a bit larger improvement in their blood pressure rate. Okay, so the men were randomly assigned to their treatment groups. For the normal condition, we have the normal probability plot of each. So this is under putting the numbers into L1 and L2 of your calculator, going to the stat plot, and choosing that sixth type of graph for each one separately. Since this is a two-sample on matched pairs, we looked at the normal probability plot of just the differences, but on this one, the normal probability plot of just the original two sets of data. Okay, the first set of data for the placebo group looks fairly linear, so you could say the normal condition is met. Make sure you are justifying it by including the graph. There is a little bit of non-linearity, like a distinct curve pattern here, so you could mention that you would have some concern about the normal condition being met for the calcium group. Okay, last condition, just once again, little practice with that. Because this is an experiment, 10% condition would not be the best justification. Better justification would just be that it is reasonable that one subject's blood pressure would have no influence on another just biologically. Therefore, the results should be independent. Okay, take a minute and look on your OneNote notes. There are a couple of examples. We're going to skip the low birth weight babies one for a minute. There are two very similar examples. One where the data is given to you, where 20 volunteers were randomly assigned either drug 1 or drug 2, so two treatment groups, versus the two drugs, 20 volunteers are paired based on their average hours of sleep without medication. What I want you to do is pause the video for a minute, take a look at the two scenarios, what the main difference is in between them, figure out which one would be matched pairs, which one would be two sample, and write down real quick what the differences in how you would carry them out would look on your state plan, do, or conclude steps. So the first one in OneNote, where they were randomly assigned to either one or the other of the treatment group, that would be considered a two-sample t-test. Okay, so I have two treatment groups. I have 10 in each, but it does not say anything about them being paired. So I have the mean and the standard deviation of each group separately. My hypotheses would be that mu1 is equal to mu2 versus mu1 not equal to mu2. In other words, there's some difference in the effectiveness of this to help people with insomnia. Carrying out my, I should have also written this down, carrying out my conditions, I would need to check each condition on both of them separately. So I would have to graph drug 1 and drug 2 separately on two different normal probability plots or histograms to check for the normal condition. I would need to make sure that both of them the groups are randomly assigned, so that's met, and state that the insomnia or the restlessness of the patient should not affect one another. In other words, they have to be in separate rooms, so they're not, one person's wakefulness is not bothered by the other. But in other words, I have to do it for each group. For my results, I ended up getting I failed to reject the null, which suggests that there is a difference between the effectiveness. On this other one, I have matched pairs, so it would just be a one sample t-test. My Mel will be